In 2015, two men drove a Volkswagen across the continental United States on just over 100 gallons of fuel. Their 81 mile per gallon performance doubled the car's estimated fuel rating and set the record for the lowest fuel consumption ride of the diesel car. The duo called themselves hypermilers and are experts in techniques that maximize the car's fuel efficiency, such as the pulse and glide. In the pulse, drivers accelerate slowly until they are traveling slightly above their intended speed. They then slowly release the throttle and glide until they are slightly below and repeat. To understand why this strategy saves fuel, we first need to unpack what exactly is going on beneath a car's hood. Non-electric cars run on internal combustion engines, or ICEs. Cars are often advertised as sporting a 4, 6, or 8-cylinder engine, which refers to this device's main components. Within each of these cylinders is a piston, which moves up and down, spinning a bar known as a crankshaft, effectively converting the linear motion into a rotary motion that can drive the wheels. What powers these piston movements is what gives these engines their namesake, combustion. As the piston lowers, air and fuel are sprayed into the cylinder's chamber. Then, as the piston rises, this air and fuel mixture is compressed. In gasoline engines, a spark is introduced, igniting the gas. In diesel engines, the compression alone creates mini explosions. This combustion causes an immediate increase in temperature and pressure, propelling the piston down as it starts the cycle again. The gas pedal controls the amount of air and the subsequent fuel released into the chamber. The more fuel in the chamber, the more powerful the combustion, making the crankshaft rotate faster. Driving down the highway, ICE cars spark thousands of blasts per minute, but explosion power driving is pretty inefficient, as much of the energy generated is lost to heat. In fact, only 16 to 25% goes toward the moving a wheel. These explosions also create CO2, and ICE engines produce 15% of the total global carbon emissions. The pulse and glide can increase efficiency for two reasons. First, when accelerating to higher speed during the pulse, the engine works at a higher efficiency compared to traveling at a constant lower speed. And second, modern car engines shut off fuel injection or idle when decelerating, meaning that as the car glides, the wheels are driven by inertial energy rather than combustion, ultimately saving fuel. But even at the peak performance, ICE hypermilers can't compete with the true champion of the fuel efficiency rise, the electric vehicle. Many EVs run on induction motors, which have two main parts, a stator and a rotor. The stator is a series of rings with copper wires wrapped around it. By conducting electricity at variable rates, these wires create a rotating magnetic field. This field induces the rotor with electric current, causing it to spin and driving the motion of the wheels. For EVs, pressing on accelerator changes the frequency of current driven into the wires of the stator, in turn increases the rate at which the rotor spins. By utilizing battery power rather than gasoline, 65 to 69% of energy consumed by EVs goes directly to moving the wheels. And since EVs don't create explosions, fewer parts are needed below the hood, while a typical ICE vehicle has over 2,000 moving parts to help contain, cool, and maintain combustion. A typical EV has about 20. EVs are completely changing the hypermiling games as drivers compete to travel the farthest on the fewest kilowatt hours. And the records will likely only get more impressive as the design of EV motors allow for the introduction of innovative energy-saving devices. For example, most EVs utilize regenerative braking, where energy normally lost to friction is conserved. As the car slows, the electric motor operates in reverse, capturing the vehicle's kinetic energy to recharge the battery. Some companies are even equipping EVs with rooftop solar panels, further increasing their range. Since they don't burn fuel, EVs have zero tailpipe emissions. That's not to say they're always carbon neutral. EVs requires regular charging of their batteries, meaning their emission profile is only as clean as the electrical utility they plug into. So as the global grids continue to shift towards renewable sources, EVs are also becoming greener, making them an even more attractive, hyper-efficient option.